Well, in this short video, I'm going to show you maybe for the first time something known as a differential equation and how these can be used as one way of describing a simple harmonic oscillator or an object in simple harmonic motion. Let's see how this works. Now I found some equations that you should recognize as ways of describing the position, velocity, and acceleration of a typical simple harmonic oscillator. Now, some of these are written a little differently. For example, you'll see here dx dt, but of course dx dt is just another way, a calculus-y way of writing a velocity. And the second derivative of x with respect to t, that's the second derivative of position, is another way of writing acceleration. So that is the x, v, and a equations. You notice here we're using the letter a for amplitude rather than x max, which is used often in other sources. But everything else should look very typical. So if you recognize here the last part of the acceleration equation, the a cosine omega t, notice that that's exactly the same function that we have up here. There's one little difference in that this one includes a phase constant. I'm just going to tell you for now, without any kind of proof, that whether or not that's in there does not make any difference. In fact, I might argue that these equations should probably all be written with that phase constant in there. The source that I grabbed this from just didn't have it. I didn't feel like trying to write it any differently. So we can just replace the a cosine of omega t with what it represents, which is just the position. And so if we do that, I'll show you what we end up getting. It says that the acceleration, or the second derivative of x with respect to time, is equal to the negative of the omega squared times the position itself. Now, this looks very mathish and may not make a whole lot of sense, but let me just tell you in plain language what this means. It means the acceleration of an oscillator is related to where the object is that's oscillating. So if you just think of a typical mass that you might be hanging from a spring and you see it bobbing up and down, well, when that mass is right at the extreme of its oscillation, so at the very top or at the very bottom, that's actually where it's accelerating the most, because you see sort of a direct relationship here between the acceleration on the left and the position. But where the acceleration, or where the position rather, is zero, like right in the middle of the oscillation, that's actually where at one moment the forces are balanced. You actually have no acceleration right there. The negative sign tells you that when the object is at its highest most position, that its acceleration is the most downward. That would be where the spring is very squished. But where it's maybe at its lowest position and the spring is most stretched out, that's where it would have the most upward acceleration. So the position and the acceleration are always in opposite directions. And then of course they're not equal to each other, but they are related by this value that we call omega squared. And so every simple harmonic oscillator can be written in some form like this. If it's a mass on a spring, then the omega squared takes the form of k over m. And so we could put that in there. So this is what it would look like for just the bobbing mass. And there are other forms as well. This would also work if you had just a frictionless surface with a block moving horizontally. We're going to see other forms like this as well for a pendulum, for example. There's different kind of pendula that work this way. So anytime you see an object whose motion can be described with a second derivative of position on one side and the position function itself on the other side, you'll know you always have something in simple harmonic motion. So differential equation, again, maybe the first time you've seen something like that. You know, you've heard of other kinds of equations. For example, a quadratic equation. Quadratic equations have terms in them that are quadratics. That means they've got squares. Or a cubic function. Cubic functions have cubes in them. Or you've heard of cosine functions. They have cosines. Well, this is just called a differential equation because it has a derivative in it along with the original function. So just a new term, but not anything to be afraid of. So hopefully when you see this kind of equation written, you'll know exactly where it comes from and what it means. And we'll hope that on an AP test you can recognize something like this too, because you're bound to see that.